Hello, everyone. So today we will be looking at a very important concept from our chemistry syllabus, the physical properties of aldehydes and ketones. Let's begin.
I want you to think about something you have surely experienced. When someone opens a bottle of nail polish remover, even from across the room, you can smell it almost instantly, no? And if a little bit spills, it just vanishes in a few seconds. Why do you think that happens?
Well, the answer to that question lies in their physical properties. Once we understand what is happening at the molecular level, we can understand why they behave this way and why they are such useful and, as we saw, volatile solvents in our daily lives.
So, what is the big secret behind these properties? It actually comes down to one simple idea: polarity. You can think of these molecules as having their own little magnetic fields.
At the simplest level, it all starts with the carbonyl group. That is the carbon-oxygen double bond, CO. Now, this bond is polar. Oxygen is more electronegative, meaning it pulls the shared electrons more strongly towards itself. This pull creates a small separation of charge, turning every single molecule into a tiny magnet. And this molecular magnetism leads to a specific kind of intermolecular force. The proper scientific term for this is dipole-dipole interaction. It is simply the weak attraction between the positive end of one of these molecular magnets and the negative end of another one nearby.
This is a very good analogy to remember. Just imagine you have a box full of tiny bar magnets. They will naturally try to arrange themselves so that the positive end of one magnet attracts the negative end of its neighbor. This is exactly what is happening inside a liquid aldehyde or ketone.
So let's be very clear about what is happening at the atomic level. The oxygen atom, because it is pulling the electrons closer, gets a small negative charge. We represent this as delta minus. This leaves the carbon atom with a small positive charge, or delta plus. The separation of positive and negative charge is what we call a dipole.
Okay, now that we understand the theory of these tiny magnets, let's build a mental picture. What is actually happening inside a drop of liquid acetone? How are all these molecules behaving together?
First, you must always remember that in a liquid state, molecules are not stationary. They are full of energy, constantly moving, tumbling, and colliding with one another. It's a very chaotic environment.
Now, in the middle of all this movement, sometimes, just for a moment, the positive carbon of one molecule will align with the negative oxygen of another. When this happens, a weak attractive force is formed, our dipole-dipole interaction. But it is very important to remember that this attraction is brief and weak. And here is the main point. The normal heat energy that these molecules possess at room temperature is actually strong enough to easily break these weak magnetic attractions. So, molecules, especially at the surface of the liquid, can easily overcome these forces and escape into the air as a gas. And this process, of course, is what we call evaporation.
Okay, so we have understood the theory of molecular magnets and weak forces. But how does this explain what we actually see and use in the real world? Let's connect the theory to the application.
This takes us right back to our original question. The reason acetone evaporates so quickly is precisely because these dipole-dipole attractions between its molecules are very weak. They don't hold onto each other very tightly, so it takes very little energy for them to break free and become a gas.
And this is exactly why acetone is such a good nail polish remover. Two of its properties are working together. First, the polar C-bond-O group helps it dissolve the polar polymers in the nail polish. You know the principle, like dissolves like. And second, because its intermolecular forces are so weak, it evaporates very, very quickly, leaving the nail clean and dry. It's perfect for the job.
Now, a very common doubt from many students is this. You might be thinking, "Sir, but alcohols also have an oxygen atom, so shouldn't they behave similarly?" But we know that an alcohol, like ethanol, evaporates much more slowly than acetone. So why are they so different?
Let's just look at this comparison. The most important difference is the dominant intermolecular force. For aldehydes and ketones, it's the weaker dipole-dipole forces. But for alcohols, it is the much stronger hydrogen bonding. Because this force is stronger, alcohols have higher boiling points and they are also more soluble in water.
So the single most important difference is the presence of the OH group in alcohols, that is, a hydrogen atom bonded directly to an oxygen atom. This special arrangement allows alcohol molecules to form strong hydrogen bonds with each other. Aldehydes and ketones have a C equals O group, yes, but they do not have an OH group. Therefore, they cannot form hydrogen bonds among themselves. This is the fundamental difference. All right, that was a lot of information. So let's quickly recap the most important points that you must remember for your exams.
So, there are 3 key takeaways. First, the starting point for everything is the polar nature of the CO bond. Second, this polarity creates weak dipole-dipole forces, which you can imagine as tiny magnets attracting each other. And third, because these forces are weaker than hydrogen bonds, aldehydes and ketones have lower boiling points and only moderate water solubility compared to alcohols.
So, my final advice is this. If you can just remember the simple picture of tiny magnets, and if you remember that the main difference from alcohols is the lack of an OH group, this entire topic will feel much, much lighter for you during the exam. I hope this was helpful.